there in Novi Sad.
Я не знаю точно, что там написано. Я не был там, вот не видел.
Я знаю, там написано Милева Марич, мать квантовой механики.
Ну, это много.
And I know what is written there. Mileva Maric, the mother of quantum mechanics. Yes.
Давай предложение не обсуждать сейчас. Уже у нас мало времени.
И без этого хлопот хватает.
Хватает, мало ли кто-то, конечно, что написал. Да.
Henrik, hello. Hi, Henrik. No problem. I will make you co-host now, so you can share. Just a second. Make co-host. Okay, I think now you can share the screen.
Okay, good.
How are you?
I'm good. Just doing some last-minute edits. That's why I was a bit late. Yeah.
Okay, hold on.
Hold on. Okay, I'm in the wrong slide. Let's check. Okay.
We can start in 1 minute, 1-2 minutes, because people usually come last moment.
See, can I make it full screen also? Let's see.
Yes, name is better.
Okay.
Perfect. Cool.
And you see, let me also switch to the next slide.
You also can try your cursors, because sometimes there are problems with cursor.
Yeah,
we can see it. We can see it.
Okay, and nothing is covering the text anywhere? Or?
No, yeah, everything's fine.
Okay, good. Can you just go and get some water? Well,
yeah, sure, of course.
Ира, вы сейчас на работе?
Да, я на работе, потому что тут надо финансовый отчет сдавать.
Я вижу.
Вот.
И узнаю эти полки за вами.
Да, и мне обещали сделать к 6, но так и не сделали, так что я сижу здесь вот.
Прекрасно.
Да.
Eric, is it okay if people ask questions with the talk, or you prefer?
Oh yeah,
at the end?
that would be fine. Yeah.
Okay, cool.
Okay. How many people? Между прочим, я сегодня была утром на очень интересной конференции, посвященной столетию Глинера. Очень жарко. Я бы вот не сообразила.
Maybe let's switch to English, maybe.
Okay. This morning we had a special seminar dedicated to Professor Gliner from St. Petersburg. But it was very, very interesting. He was one of the first person who proposed for inflation. Yes. Okay, maybe it's time now to start. It is my pleasure to introduce Henrik Johansson from Nordita. He will tell us about scattering amplitudes for Kerr black holes and high-spin gauge symmetry. Please, Henrik, 1 hour.
Thank you very much. It's a pleasure to be here at Quantum Gravity and all of that seminars. I wish I knew about this. I would probably have joined some other previous talks, which look very interesting. But it's a pleasure to be here. So I will talk about some very recent work. In fact, the latest one of my references is just from December. So it's a fairly new topic. And this is my first talk on this topic, so I maybe apologize in advance if it's a bit rough. Now let me start by some motivation. This talk is not really about gravitational waves, but the motivation for the work I've done comes from gravitational waves. So let's start with that. As we know, there's a lot of interesting physics, astrophysics coming from gravitational waves at the moment and also in the future. What I'm interested in, and what many of my colleagues is interested in, is actually to try to understand this in-spiral phase a bit better, because there's a lot of physical information there. In particular, future experiments like LISA, those experiments are just going to see this in spiral phase in many cases, and they might not even see the merger. So if you want to extract physics, we should maybe focus on this part. And essentially, you need to know it very accurately, because you can, for future observations, you might see you might see this phase over many cycles, and so any error that you have in theory will accumulate. So that's a very important aspect. So this is basically the post-Newtonian region where the black holes are well separated. So I have some details here. I'm not going to really go through the details, but essentially the name of the game is to try to understand orbital mechanics in some effective theory, construct some effective Hamiltonian, which may look like this. I have just included the first few terms here. But there's alternative expansion scheme, which maybe is more familiar from people doing more, Feynman diagrams or doing something related to QCD, and that is called the post-Minkowskian approximation. And the post-Minkowskian approximation is essentially not doing a velocity expansion. So here in the post-Newtonian one, you're sort of assuming that velocity is the same as the energy by the virial theorem, and therefore you're somewhere in this slice here. Whereas when you do the post-Minkowskian approximation, the velocity of the objects can be as large as you want, and that in principle includes scattering, right? So which is sort of in this corner. And here's some roughly schematics, how it looks like when you do the post-Newtonian versus the post-Newtonian approximation. So as I said, the PM expansion is essentially expansions in Newton's constant. So from the Einstein-Hilbert action is kind of straightforward. What you're doing, you're just expanding in gravitational coupling. Whereas when you do the post-Newtonian one, you're sort of moving along some kind of diagonal here. You're trying to capture things which are the right order in velocity. So basically, you do this one, this one, this one, and this one, and so on. And I have circled roughly where state of the art is currently, and I have listed some references here. And maybe I'm a bit unfair because there has actually been quite a lot of work on 5PN, and also I think also maybe something towards 6PN, and there's also been 4PM work, but maybe not complete. But this is roughly where we are. And as far as I understand, we need to go several orders higher for future experiments. Now, what I really want to talk about today is having to do with spin, and that brings another sort of dimension in the parameter space, and that's the spin multipole expansion. So the spin multipole expansion is essentially saying that we can approximate a spinning object by its spin multiples. And for example, the monopole is simply the non-rotating black hole. And then the dipole is the first approximation, and this is essentially linear in the spin vector or the spin tensor or whichever variable is being used. So here I given one approach to this problem, essentially developed by Levin Steinhoff in the mid 2010s, or I think 2015, and that's essentially to write down a point particle whirl line action for the matter system. So the matter system in this case is a black hole. Whoops. So essentially you write down some standard whirl line action, which is this piece. Then you add something which carries the spin degrees of freedom. So this is angular parameters, and this is essentially the conjugate variable, which is the spin tensor. And these are the sort of the two obvious terms that you write down. But then there's a whole bunch of non-minimal interaction terms. So SI stands for spin interaction terms. And these are in general not well understood. However, these authors did write down an infinite number of them corresponding to leading order interactions, but for any order in the multiple expansion. But I'm not going to show the details, but I will come back to it later on. And then if you start from this action, which is you take basically as your defining action for what you want to compute, then you define in turn you compute something which is the effective Hamiltonian. So in this case, you get, for example, spin-orbit couplings at leading order, and I have just shown a few terms here, and I'm not trying to explain what the notation is, but this is something that kind of looks familiar from ordinary quantum mechanics, where you start adding spin orbit and spin contribution, etc. And you can also convert between the spin tensor and the spin vector. Spin vector is essentially the same as the Polar-Lubansky vector. And also I included a table here. This table is coming from this recent paper by Michel Levy and Jin. And I'm not going to try to explain what it is, but it gives a rough understanding for when you look at the spin multiple moments and you compare to essentially orders in the gravitational coupling. You can get a feeling for what P-n order does that correspond to. And you can see that at leading order, which essentially later on is going to correspond to tree-level diagrams, things can be done to very high P-n order, or if you're doing the non-spinning case, you can also do it to very high next to leading order, but it's the case is sort of in between, which is more complicated. All right, so that was the review I was going to do about P-n and P-m calculations, and so now I'm going to do more amplitudes perspective here. So this is for those of you who have followed amplitudes field, this is more about trying to understand just scattering amplitudes in gravity, to do, for example, studies of UV behavior, etc. So one thing you learn when you start doing calculations in GR is that it's very complicated. It's not like QCD. QCD is difficult, but GR is at a whole different level. And this, you get a flavor for this when you start writing down the Feynman rules, which DeWitt did in his paper from 1967. Propagator is maybe not so complicated in the donor gauge, but then you start looking at the cubic interactions, and here I've written them in a compact way using some permutation symbols and symmetrization. But if you actually write down all of these terms, there's an order of 100 terms just in the cubic vertex. If you look at the quartic vertex, you get on the order of 1,000 terms and so on. And maybe it's not terrible, but when you start multiplying these vertices together, then you really get multiplication of large number of terms, and it just grows factorially and becomes really bad. For example, I spend some time doing some multi-loop calculations in supersymmetric gravities. But for example, one of the first calculations I looked at was 3 loops, there, if you just do the naive counting, which is maybe a bit too naive, but you just do the naive counting of multiplying 100 terms in each vertex, you get the rough order of 10 to the 21 terms, which is it's a astronomical number. So it's naively seems very complicated. But I also want to say that in the last 2 decades or so, or maybe even 3 decades, we have realized that things can get much simpler if you're trying to understand things which are more well-defined than off-shell vertices. You look at things which are defined on-shell, things which are gauge invariant, things which do not have ambiguities due to diffeomorphism symmetry and so on, and you find a lot of simplifications. So here, for example, just looking at the plane wave, you can see that the plane wave of a graviton is simply factorized into 2 Yang-Mills polarizations. If you look at the on-shell 3 graviton vertex, which you can study, You have to study it for complex momenta, but as an analytic function, you can study it. You notice that on shell, it will factorize into two vertices, which are familiar from just Yang-Mills Feynman rules. And if you look at the 4-point amplitude, which is the first physical process that you can have for real momenta, you notice that if you just hit full simplify on your Mathematica, you will notice that it will actually factorize into a square, and inside this square you will find the Yang-Mills trio-level amplitudes times some overall Mandelstam invariance. And these are part of this remarkable simplifications that the gravity S matrix satisfy, and they go under a couple of different acronyms. So the original one is Quayle and Tai. There's Bernd Henrik Johansson, which I guess is me, and there's Cachaso, He, and Juan, which is the most recent incarnation of this structure. Let me just briefly mention the Quayle and Tai, because this comes from string theory, and it's from early work in the mid-1880s. 1980s, wrong century. Sorry about that. And the basic idea there is that from the whole construction of string theory, you can think that closed string has to be some product of a left moving open string and a right moving open string. I think it was understood fairly early, but what Quayle and Tai did is that they show that this heuristic property, it also survives after you have computed your tree-level S matrix. I'm not really going to show the details here, but let me just show some what happens when you take the field theory limit. So in the field theory limit, these Quayle and Tai relations, they become a relation between tree-level matrix element of gravity and tree-level matrix elements of Yang-Mills. So in the simplest one, which is the 4-point one, is a simple product. Starting at 5 point is a sum of products, etc., etc. And this works essentially for all the states which are there in string theory. So it works for spin 2, it works for spin 3 halves, etc., etc. So it's a fairly general structure. And then let me also say something about this BCA double copy, which is something I worked on. And so what we did here is that we simply reformulated this squaring of gravity. And so we simply reformulated in terms of the cubic diagrams. They're not exactly the Feynman diagrams, but you can get them by simply massaging your Feynman diagram. So you can take the Yang-Mills Feynman diagram, and then you can square the numerator. You should not square the poles, but just the numerator. And then you can observe that if you do it in the right way, which is, it's a tricky thing to do, but if you do it right, you will get Feynman diagrams of gravity. It doesn't come directly from some Lagrangian, but it has the right properties. It has diffeomorph symmetry and so on. So it's a theory of gravity. And this can be generalized to loop level. So that's the new feature of doing it in terms of diagrams, is that it has generalization to loop level. This has some annoying feature from the point of view of getting just pure gravity. I don't know, can you see my menu? Maybe
Yes, we can see your
yeah, this kind of covering things, but I don't know how to.
No, we don't see anything.
Oh,
It's
okay.
covering. Yeah, it's fine. Yeah.
Okay, it's covering on my side, but that's okay.
Ah, okay.
Yeah. Anyhow, so if you want to get, for example, if you want to enter pure Yang-Mills here, so just pure gluon, any number of colors, it doesn't really matter. Then you get Einstein gravity plus a dilaton in a 2 form. And in 4 dimension, this just becomes 2 scalars. Sometimes this is slightly polluting your calculations, but for example, if you just work at 3 level, this extra states can be decoupled, so that's not a problem.
Sorry, Henrik.
Yep.
Are there exact formula for all these relations also for m-point amplitudes?
Well, it depends what you mean by exact formula.
Some closed form, like when you say
there's a prescription. That's a prescription that if you do certain things, if you satisfy certain relations, then it will always work, right? But the tricky part is satisfying those relations, right? So these relations are what we call kinematic Jacobi relations, right? And they're not coming, they do not come out automatically from Feynman rules, right? So so essentially what you have to do is you have to compute your Yang-Mills in some gauge or by some other means, by some ansatz, and then you have to hope that you can massage it into the right form such that it satisfies the relations, right? And so that's a non-trivial aspect. It's not proven that you can do that at loop level in general, but there are many examples where it works. But given that you can satisfy those properties, then is coast is clear, right? And it will work, right?
Okay, I see. So there is a question in the chat. I don't know if you can see it, otherwise I read it.
Yes, yes.
I can also read it if you cannot see it.
Yes, yes, that's a very good question. So certain modifications of GR with higher curvature terms do still give a relation between gauge theory and gravity. Of course, you have to add corresponding higher derivative terms in the gauge theory. And the obvious way that you can see that this has to work in some way is that that's precisely what string theory is doing, right? String theory is already adding higher derivative corrections to the gauge theory and the gravity theory, and they're related through the KLT formula, right? But the full extent to which this can be done or not done is not understood. That's still, people still writing papers about this, right? So it's not clear that you can map every higher derivative operator in gauge theory to gravity and vice versa. That's not at all clear, yeah. All right, so much about reviewing old stuff. So now I'm going to try to get some new stuff. So this is the outline of the rest of my talk. So I will talk about something that I call AHH, higher spin amplitude. So AHH stands for Arkani Hamed Huang. And I will tell how that they're very interesting higher spin amplitudes, but they have some problems, and the problem has to do with Compton scattering. And that's where it's going to be relevant for Kerr black holes, as we're going to see. And then I'm going to describe some EFT understanding of where these amplitudes come from. And that's going to lead me to higher spin gauge symmetry. But yeah, hopefully I get to the end of the talk. So let me start by this Arkani Hamed Huang amplitudes. So it all began in 5-6 years ago when Arkani Hamed Huang wrote down some seemingly very simple amplitude using a notation that people call massive spinor helicity notation. It's a bit of a misnomer because there's no helicities when you have massive particles. But it comes from the fact that there is a massless formulation, which is called massless spinor helicity, and this was simply a generalization of this. I will briefly explain the notation later on, but for now you can just think of this as some Weyl spinners, on-shell Weyl spinners. So this is the chiral, and this is anti-chiral spinners. X here is not a space coordinate; it's just a fudge factor, or it's basically an overall factor that this guy's introduced. So I'm just using their notation. So this is an amplitude between two spinning objects of the same spin, and then a graviton of helicity plus or helicity minus. And you can see here that if you take, for example, the spin to 0, then simply this X factor is essentially the amplitude between a scalar and a graviton. And I will come back to that later on. So why am I showing these formulas? It's because these formulas are very interesting from many points of view, which I will come back to. But let me first show another result, which was also written down the same year. So Justin Vines wrote down the stress energy tensor for the source of a Kerr black hole. Now, that might sound a little bit ambiguous, maybe, because often we think of the Kerr as a vacuum solution. But anyhow, Justin Vines thought about it for a long time, and he wrote down a formula, which is the linearized energy momentum tensor for a Kerr source. And what's noteworthy about this formula is that it involves an exponential. This start product here is simply a dualization with the Levi-Civita tensor. This is the spin tensor, which I had on some previous slides, and I will come back to it. This is the mass of the black hole. This is the momentum of the black hole. All right, now a third formula, which was presented 2 years earlier, which was Levi and Steinhoff. And as I said, they worked on this Wehrlein formulation of Kerr. So in their Wehrlein formulation, they had this ambiguity of a non-minimal term. And here I'm simply showing the first corrections to this non-minimal term that they wrote down. And as you can see, it's essentially a multiple expansion of powers of the spin vector. So the sum goes from 1 to infinity, and as you increase n, you get more and more powers of s. There is essentially a parity even and a parity odd contribution. So this is just why, that's the reason why there are two terms. The d's here are just covariant derivatives in the Wehrlein formulation. U here is the velocity of the Wehrlein. E and B are the electric and magnetic parts of the Riemann tensor contracted with the velocity, velocity U. I'm not going to try to explain it any more than that, but the reason I have all of these things on the same slide is that they're basically the same thing, but very different manifestations of the same thing. And that's what I'm going to try to discuss in the rest of this, or the rest of the first half of this talk. I'm not going to try to derive it, but I will derive a simpler version of it partially. Let me also review something that's called root Kerr gauge theory. It's a funny name, but it's kind of fitting name. So that's a very old story that goes all the way back to almost all the way back to the discovery of the Kerr metric, and that's that you can actually understand the Kerr metric, the Schwarzschild metric, and several other interesting metrics by looking at the metric on this Kerr-Schild form. So the way the Kerr-Schild form works is that you write down a background metric, which in this case is just flat space metric. Then you write down a sort of a linear perturbation of that metric, which involves a null vector k. The null vector k is null both respect to the full metric and to the background metric, which is possible precisely because it has this form. And then there's a scalar potential sort of a prefactor. And an interesting thing about this Kerr-Schild form is that given such a metric, you can also construct a gauge field. And this was discussed discussed in detail in this recent paper, or sorry, recent is 9 years old, I guess. And they discussed it from the point of view of the double copy. So if you read that paper, you will see the word double copy and single copy. So this is the single copy. And so this is also called the classical double copy because it's no longer talking about amplitudes, but it's talking about classical solutions. And also in more recent language, we also call this one root Kerr because it's sort of related to Kerr one by a rough square root. Maybe many in the audience know this a lot better than me, but I wrote down some relevant formula. So in the Kerr case, you can write down this scalar prefactor to be like this. And this the R here is not the usual radial coordinates, but it's related to x, y, z by this equation here. So I think it's some kind of spheroidal coordinates. Yeah, one thing maybe I should also say is that if you look, for example, at the Kerr-Newman black hole, which is charged, I think this is actually the gauge field of that solution. But as I said, I'm not quite an expert on this, so I might be slightly wrong. But speaking of Newman, another very interesting fact is the Newman-Janis shift. And here I have written it almost schematically in terms of the Newman-Penrose curvature scalars. So this is essentially a curvature scalar for the Val tensor. This is a curvature scalar for the field strength of electromagnetic field strength. But the nice feature about the Newman-Janis shift is that once you do it the right way, you can just show that Kerr is simply a complex deformation of the Schwarzschild solution, and this gauge field solution here, which we called root Kerr. Sorry, that's an error. That should be Coulomb, not root Coulomb. Yeah, so root Kerr is a deformation of the Coulomb solution, and furthermore, these are just directly related by double copy. Yeah, so this should say root Schwarzschild, not it's a typo. And why am I showing this? Well, because you can do it on the curvature scalars, and curvature scalars are very nice because they're essentially invariant. Curvature is invariant quantities. Another quantity which is diffeomorphism invariant is amplitudes. So you can do this Newman-Janis shift directly on the amplitudes. And although this might look very mind-boggling, in hindsight it's kind of obvious. You're deforming your spatial coordinate. What is it going to do to your amplitude? Well, it's basically going to deform your plane wave factor. This is a plane wave factor with where the x has been replaced by IA, right? And that's why it's actually no longer a phase, but it's actually an exponential. So that's really intriguing, right? Just from the Newman-Janis shift, we get insight to what should be the amplitudes for a Kerr black hole relative to the amplitude of a Schwarzschild black hole at 3 point. This is just for the 3-point amplitudes. And I should also specify this is what we call tree level, which means that it's lowest order in the gravitational coupling. It's also assuming that we're studying the black holes from a far distance, so we're simply ignoring anything having to do with the horizon, right? Because we're just simply very far away from the black holes. But they're related this way. And we'll see that that's a very interesting feature that has been derived several different ways, and I give some of the references below. All right, so let's go back to this Niemeyer, Akarni Hamed, Wang Huang amplitudes. And so now I show, I both show the gravitational one for plus helicity graviton and a minus helicity graviton, but I also show this, which we're going to call root Kerr amplitudes. And now we have, we can take this to be just a photon. So this is a plus helicity photon, this is a minus helicity photon. And you see that they almost look exactly the same. The only thing that differs is this X factor. This X factor carries the helicity of the massless particle. So that's why you see that it's squared here versus not squared there. Anyhow, so one thing that you might ask right away when you see these formulas, and I said that they were related to the other formulas which had the spin multiple expansion. And also I claim that these are somehow related to the Kerr. So the question is, where in these formulas do you find the spin vector, right? Or for that matter, where do you find the ring radius of the Kerr solution? Where is it, right? I mean, there's no A, there's no S. Likewise, where's the exponential factor, right? This is a power. This is a simple power. How did it become an exponential, right? Furthermore, one thing to note that these are quantum amplitudes, right? These are a quantum spin, discretized spin, whereas Kerr has continuous angular momentum, right? There's nothing, as far as we know, there's no discretization in GR of the angular momentum, right? So what are these quantum theories, right? I mean, this is a quantum S. So that's what we're going to try to answer in the next few slides. So let's start with the first question. So in order to answer that question, where is the spin vector? We're going to try to introduce the spin operator. So spin operator is, the usual operator in quantum mechanics that you use to, you do your SU2 algebra and so on. So let's try to do that. So we're going to start by simply thinking about how do we parameterize SU2. So SU2 is essentially the tree sphere, has the same, well, it's the, sorry, I'm getting lost here. The group manifold, that's the word I was missing. The group manifold of SU2 is essentially the tree sphere. So we can start with this Z variable, which depends on 4 real variables. And then we can say that let's use the, just complex conjugate it, contract it, and say that it's equal to 1. That gives the equation for the tree sphere, right? The norm of these 4 vectors is equal to 1. But we can also think of this SU2 as some fundamental representation of SU2, right? This is just an SU2 index, right? And in fact, we're going to see that this we're going to think of this as the spin components. It's going to be the upspin and the downspin in standard quantum mechanical language. Now, I'm going to write down a formula which relates the spin vector, which is now it's a 4 vector rather than a 3 vector, and this Z variable, which encodes the SU2. And I already showed you these spinners here, and this is a part of the massive spinor helicity formulas. I will have one slide shortly which will explain a little bit more, but this is just Pauli matrices, or this is the spin quantum number. This is the mass of the particle that we're interested in. The reason there's a 1 here is not a unit element. It just means that this is particle 1 when we do the scattering. So that's why I wrote the 1 there. Before I explain a little bit more the spinners here, let me just say what are the properties of this object here. So first of all, if you contract in momentum 1, so the momentum of particle 1, it will sandwich between spinner 1 and spinner 1 bar. And essentially these spinners are on-shell spinners, so they are essentially killed by P1. So that means that this spin vector is transverse. And that's a good thing, because a spin should only have 3 components. There's no spinning in the time direction, right, for a stationary object, right? So this is basically saying, things cannot spin in the time direction, in the frame of that particle, right? So that means that the spin has 3 components. That's what it's first saying. Now, the next thing it's saying is that we can also think of this spin vector as an expectation value. And the way we do that is we essentially construct a spin operator, and then we sandwich it between the state. And as I said, the state is parameterized by this up-down Z variable, right? And you can check that if you, for example, take this object here, you can take derivatives to these variables here, appropriate number of times, you get this spin operator. You can check that it satisfies the usual commutation relation. This Levi-Civita here is basically the 4-dimensional Levi-Civita contracted with the momentum P1. So it becomes a projection down to like a 3-dimensional Levi-Civita as it should be in the rest frame, right? You can also check that squaring the spin operator just gets the usual quantum mechanical square. So this is the right way to parameterize it. And you can ask, why do I care about parameterizing it? Well, we want to show an equality between something related to S, something related to capital S, right? So this is a good starting point. Now let me say something about this massive spinor helicity formalism. So I already showed you this bold Ketz and square Ketz. Oops. And all they mean is that I have a chiral Weil spinner and a left-handed Weil spinner and a right-handed Weil spinner, right? Now this is a massive, and the massive little group is SU2. That's why they also carry a SU2 index, because I'm essentially think of them as a encoding all the physical states. So there's 2 physical states. That's why it has an index 2A running from 1 to 2. And C is basically the amplitude of this particular state, up state, down state. And effectively what these spinners do is that they define a map from the Lorentz group to the little group. That's what they do. And why are these spinners useful? Well, they're useful because they entered in the formula before, and they entered in a very simple way. And they entered precisely like the spinner for particle 1, spinner for particle 2 to some power 2s. And if you actually compute this, this actually is a polynomial in these z variables. And so essentially it encodes a tensor in the little group, because you can have many powers of these guys. But given that you have contracted with this variable, it's just a polynomial. So you don't have to worry about tensor indices and so on. One useful feature of the spinor holistic formulation is that you can construct polarization vectors. So these are the physical polarizations of massive vectors. So like the W boson, for example. And you can just do that by sandwiching the polar matrices between this left-handed and right-handed spinners. And if you expand it out as a polynomial in this z variable, you can see that you will find like a plus helicity, minus helicity polarization, a plus helicity polarization, and a longitudinal polarization, right? So it captures all of this degrees of freedom. Now, why is this relevant to what I will talk about later? Is because not only can you construct spin 1 polarization, but you can construct spin s representations, and it's a very trivial. Actually, you just multiply it in an ordinary product. There's nothing strange. And one feature here is that this is automatically symmetric, transverse, traceless, which you should demand of higher spin fields. You should the fact that it's symmetric is obvious because it's just a product. The fact that it's traceless follows from the fact that these are in fact null vectors. So whenever you contract 2 of them, you get 0. And the reason why they're transverse is again because when you hit them with P is sandwiched between its on-shell spinners, and therefore it is 0 by the Dirac equation, or the Weyl equation, I should say. All right, so much for the recap. So now let's go back to checking what happens to this Akani Hamed et al. Amplitudes. So first of all, what I need to do is I actually need to relate particle 1 with particle 2. And in fact, I'm going to assume that these 2 particles have the same mass. And therefore it follows that I can actually just boost particle 2 to particle 1, and they're related, right? So that's the simplest way for me to construct particle 2. And the reason why I need to do that is because my spin vector only depends on one of the momenta. It only depends on particle 1 and not on particle 2. So when I compute any kind of quantities that eventually will involve particle 1 spin vector, I need to relate all the momenta down to particle 1. And so that's basically what I'm doing here. I'm saying that this spinner here, which depends on P2, can be written in terms of linear combination of the 2 particle 1 spinners. The reason is essentially that this is a basis of spinner, so you can always do this. Furthermore, it's essentially a Lorentz transformation. For example, you can see that when P3 goes to 0, then of course the 2 momentum becomes equal, and that's basically the statement here. The reason there's a bar here is because one of them is incoming, the other one is outgoing, so the bar just means some complex conjugation. Anyhow, so now I plug in this here. I just used that parameterization I had on the previous slide, and magically you get this formula So this formula means that you write down the spin operator, which was essentially the thing that appeared on the previous slide, sandwiched with the z variables, and you take powers of this, and you take powers as a matrix, right? This is a matrix power up to power 2s, and it has the 1 over n factorial. So this is clearly a truncated exponential, right? But in fact, it's also a full exponential. And the reason is that when you take powers beyond 2s, it turns out that the matrix is well, it's nilpotent, right? So it just gives you 0 after you're taking those powers. And the reason that happens is because this spin vector is a spin vector of representation s. And when you take more powers, then you have representation. Well, then the representation, eventually you just over-antisymmetrization some indices, and you start getting 0, right? So it's a statement of the finiteness of the representation. So, but it's true for any representation. You can just write it as a matrix exponential. And expectation value here just means that at the end of the day, you contract with these z variables, which encodes the state. Now, that's for that factor. But now let's also put back the prefactor, which was, I guess, in the formula I call it x, but it's really the amplitude of the scalar or the Schwarzschild amplitude at 3 point. And so you see that if you do that, now you can actually get exactly the same formula as for the Newman-Yanis shift. But unlike the formula I showed you before, it's no longer just an exponential of a scalar quantity. This is an exponential of a matrix and taking the expectation value, right? So if you wish, you can maybe call it like a quantum version of the Newman-Yanis shift, because you have shifted your x coordinate with an operator rather than a ring radius, right? So here, this is what I call the ring radius operator. It's just related to the spin operator over m. I should say that this argument here, that's essentially the latest version, the way we did it in the paper from December. The original argument was done by Guevara, Oshirov, and Vines. They are the ones that realized that the AHH amplitudes are describing Kerr and root Kerr. And if you look at the original paper, it's quite confusing. And I think the more recent papers are more straightforward in the derivation. But it's a very intriguing fact that we can now understand amplitudes for Kerr. And they have been matched to the stress energy tensor that I showed you on one of the early slides. The stress energy tensor was in fact computed by Vines, and therefore no surprise that he was the one who could check that this indeed does give you Kerr. Now this is the status of 3 points. As far as we know, everything works perfectly at 3 points. And so the next thing that you want to try to understand is 4 point. And so in particular, you want to understand this Compton scattering, where you have a black hole, incoming black hole, and outgoing black hole, and then it interacts with 2 gravitons. And well, maybe from a classical point of view, you would rather think of them as very high energy beams of gravitational radiation, like a laser beam of gravitons, maybe. But from a point of view of just playing around with Feynman diagrams, you can just think of this as a graviton and another graviton and 2 higher spin particles. So actually, let me point to this formula first. This formula was written down first. This is also in the original paper by Akani, Hamed, Huang, and Huang. So this is the case where these 2 graviton has opposite helicity. So one of them has a minus helicity, the other one has a plus helicity. The formula is very nice and compact, but it has a problem. And the problem is that for a certain spin, this factor goes negative and it ends up in the denominator. And that's bad because this is not a physical pole. All the physical poles are here. This is the S-channel pole. This is, well, it's the T-channel pole. Maybe this is the U-channel pole, or depending on what you call them. But this is not a pole. This is just some random stuff. And when this goes into the denominator, is bad because that's not a pole that amplitude should have. In particular, you can see that this pole or this factor goes to 0 when P1 is a linear combination of P4 and P3. So that just means some kind of coplanarity of the momenta. And there's nothing special should happen when momenta gets coplanar. So this is an artifact of how this was constructed. So the way it was constructed was via BCFW recursion, Brito-Kachasov-Feng-Witten recursion, which is an on-shell recursion. And it usually works very well when you have 3-point amplitude. You just glue them together, sum over the states, and then if you do it the right way, you get the 4-point amplitude. But clearly here, they did not get the right 4-point amplitude. And that's also why they showed this amplitude. They pointed out that, you know, we have very interesting 3-point amplitudes, but the 4-point amplitude has a problem. And this is why they showed this formula. Interestingly enough, they did not show the case where you have equal helicity. And so that was in a later paper. But this formula is actually perfectly fine. This has no spurious poles for any S. Of course, it has a pole in the mass, but that's to be expected. You cannot take mass to 0. And so this is a perfectly fine formula for the equal helicity amplitude. And I should say that these amplitudes will actually feature in classical calculation. These are not classical amplitudes yet, but they will feature in classical amplitudes because what you want to compute is you want to compute the effective potential between two very massive spinning black holes. And so there are contribution that looks like this, which you can essentially capture by just the 3-point formula, because it's essentially a 3-point vertex, 3-point vertex. But here you have a 4-point vertex, and the information of that 4-point vertex is contained within the Compton amplitude, right? The Compton amplitude, yeah.
Sorry, please finish, Harry. I will ask.
Yeah, I was just going to say the Compton amplitude is a sum over cubic diagrams, and a contact term, right? So the contact term is the one that's needed here, and clear. What's going on here is actually that this is an indication that you have the wrong contact term. You basically have a unphysical contact term. So yeah, that is what needs to be figured out. Okay, let's. So in this until now, basically, also in this slide, it's just S matrix approach, right? There is no Lagrangian from which you can derive these Feynman rules. Yeah, not yet. Well, sorry, let me take that back. So this one, this formula has been derived from Lagrangian, actually by this guy, not this guy, that's me. But this guy did it, and together with Zhenya Skvortsov, and what they did is that they wrote up a chiral Lagrangian, chiral formalism, and in that formulation. So this is basically a formulation which does not treat left-handed particle and right-handed particle the same way, but it makes a preference. And in that formulation, this turns out to just be generated by something that looks like a scalar theory, and all the spin content is essentially encoded in the external polarizations. So yeah, so there is a Lagrangian for this one, but in some sense, it's maybe too simple. Yeah, and it doesn't.
So it would be a Lagrangian for a higher spin field.
It's a higher spin chiral theory, and like people almost never work with chiral theory. So think of it this way. So normally when we work with vectors, we work in the 1/2 representation of the Lorentz group, right? But you can also work in the 1,0 or 0,1 representation, right? And and that's yeah. They never teach you that in school, right? Because it's not, you're not supposed to do that. But if you do that, they actually got this formula.
Okay.
Yeah.
And of course, as you said here, it's just I mean, you want to really reproduce the black hole scattering. I mean, black hole scattering. But for instance, let's suppose you want to consider scattering between neutron stars, very compact neutron stars.
Yeah.
What would you modify? Like, of course, I mean, you would imagine some different multiple expansion, but then
already at the 3-point amplitude, there might be modifications. Well, actually, I'm not 100% sure that's. Yeah, maybe that's wrong actually, but let me say it like this instead. So there are finite size corrections to the neutron stars, for example, due to tidal effects. So that they're called love numbers, for example, and the simplest one is essentially proportional to r squared in the world line effective field theory, or it essentially looks like a Gauss-Bonnet term from the world line point of view. What's interesting is that it has been proven that particular Wilson coefficient is 0 for black holes, right? It's only there for neutron stars. And there's a similar argument slash proof. So that was, the first case was for Schwarzschild, but there's a similar argument slash proof for Kerr. But it's still being debated in the literature, as far as I understand. But I think lots of people say that it is expected to be 0 for a Kerr black hole, right? So a Kerr black hole and Schwarzschild black hole has very interesting features that many of their Wilson coefficients are 0 compared to neutron stars, right?
Okay, I see. So you will get some different amplitudes in the end. In this case,
definitely for the Compton, because it's proportional to r squared, which basically means 2 gravitons, right? And that's why I took back what I said before, because I'm not sure if there is a linear in r correction for neutron star. I think there's probably not. But I'm not an expert, so maybe somebody in the audience knows better.
Yeah, I can comment about that just really quickly. There's no tidal corrections for neutron stars, but there are what are called spin-induced multipoles. So Henrik showed the spin exponential. That's only there at 3 points for black holes. If you have a neutron star, then in this power series, like if you expand the exponential on a power series, every term in the power series has its own coefficient for a neutron star. So then these amplitudes, as Henrik is saying, these amplitudes at the Compton level acquire r squared corrections, but they also will have a different factorization properties, because the 3-point amplitude is also different.
Right.
Okay, I see. Thanks.
I also see there's a question in the chat. Somebody says I'm confused. Well, I agree. It's a confusing point, but it's. We have the amplitude, but we don't have the theory, and that is what I'm trying to figure out. What is the theory, right? Now you might ask, how was the amplitudes obtained if the theory is not known? Well, it turns out that it's often the case that just based on symmetries, on-shell symmetries, so the little group symmetries at 3 points, you can actually constrain. You can constrain an ansatz for your amplitude. For example, in the massless case, you can uniquely write down Yang-Mills and gravity amplitudes at 3 points. It's just uniquely given by the symmetries of the little group. For massive case, it's a little bit harder. But what Akarni Hamed, Huang and Han did is that they wrote down a few cases, and then they saw a pattern, and they generalized the pattern. As far as I could tell, that's how they did it. And maybe I forgot to mention, the reason why they wrote down these formulas had nothing to do with black holes. They just wrote down the formulas because they thought they were nice, and they also said that this was the most natural amplitudes. And later on, it was realized that, well, they did describe kerr black holes. So I guess they were right that they were the most natural ones. But it's still a mystery. What is the theories? And so I will, in a couple of slides, I will address what are the theories, what are the Lagrangians in the few cases where we know them. Okay, good. So as I pointed out, there's this spurious pole, and I just wrote it here again just to make it clear. It's actually in the denominator when the spin is larger than 2, right? And that's bad. So this is the Kerr case. Let me also say that we should also consider the root Kerr, which I defined earlier, right? And it's almost the same. I mean, maybe you didn't even notice that this slide changed, but that's because the formulas are almost identical. The only thing that changed was this factor here. It changed from a 4 to a 2, as you see. Also, the pole changed. And this factor 2 here changed to a 4. But so the same problem is here. The same spurious pole is there, but now, unlike before it was a problem when spin was larger than 2. Now it's a problem when spin is larger than 1. And of course, if you know anything about higher spin theory, this should ring a bell, because this is precisely higher spin theory. This is a higher spin gauge theory. Higher spin means we're above the spin of the usual massless force carriers, right? And likewise, when we're in a gravitational theory, this basically means that your higher spin particles has higher spin than the graviton, and that's the problem you're seeing here, right? Something new happens when you go above the usual highest spin. Okay, so now let's address this question. What are the theories? So I used the word EFT just to not try to sell. I'm not selling that these are some fundamental theories. These are some effective description of the Kerr amplitudes. Essentially trying to, we're trying to replace the source of the Kerr metric by some field. And so that's the way to think about it. And so they're effective in some sense, meaning that this work to a certain degree, but it's going to fail at some point, right? All right, so the easiest way to spot what these amplitudes are is actually to rewrite the amplitude in terms of more covariant standard polarizations and momenta, right? So if you start with this spin zero case, which earlier in the talk I just called X because that's what Akane Hamed and company called it. But it's essentially just the ordinary Feynman rule between a scalar and a gluon. So I'm just going to call it A55A. It's just a usual Feynman rule. If you look at the spin 1/2, just a usual Feynman rule between 2 fermions and a gluon, or a photon in this case, I guess. It's just completely standard. Now, if you look at spin 1, it's slightly more interesting. So the spin 1, you might recognize this combination here. It's actually exactly the same expression that appears for Yang-Mills. Oops, sorry about that. This is exactly the Yang-Mills amplitude in covariant notation. Usually there's 6 terms, but I have used a momentum conservation to turn it 3 terms, and then there's a factor 2 there. So this is Yang-Mills, but it's also the vertex for a W boson interacting with a photon. When you spontaneously break SU2, the 3-point amplitude looks formally the same, except that momentum is now massive, right? So let's call it the W boson because 2 of them are massive, and the third one is massless, so that's the photon. And I said this is slightly interesting because this is actually not your minimal theory. This is a non-minimal coupling that you have in the W boson case. It's not, these 2 cases are minimal coupling. Now we can also look at the spin 3/2. That's also recognizable. Maybe not to most people, but if you think about it hard enough, this is probably a gravitino. And in fact, you can look in the supergravity literature, and indeed, this is a gravitino in a spontaneously broken supergravity theory, also called gauged supergravity. So it's a gauge supergravity because this is a coupling between a photon and spin 3/2. So right, so this is the gauged, it's the U1 particle in a supergravity theory that has been gauged, and then you get this interaction, and so again, it's a standard interaction in supergravity theories. What's slightly non-standard about it is that it has 1/m factors, right? And you might say, well, supergravity doesn't have 1/m factors. Well, it does have. It's just that it's m Planck rather than the mass of the particle. So this is proportional to the supergravity amplitude, and the factor is m/m Planck or whatever. It's but otherwise it is a standard amplitude, a standard theory. And in fact, I could write down Lagrangians for all of them, but I mean, you know what it is. It's minimally coupled scalar, minimal coupled fermion. This is the same interaction as in the standard model. This is the same as in a supergravity theory. And it has to have at least n = 2 supersymmetry for this to be possible. Otherwise, you don't have a gravity photon. Anyhow, what about for general spin S? Well, for general spin S, I don't know what it is, but I can write down the covariant formula, right? So that's something we did in this paper from 2001. We say that, well, I don't want to write down every possible case. So let's instead construct a generating function. Let me just sum over all of them. And you can always undo the sum because basically they have different powers of polarization. So it's pretty easy to see which term corresponds to which spin. And then you can see that, well, this is the first term, which was just a scalar. This is the next term, which is just a W boson. And then you get other interesting combinations. But you also see, for example, that there is this term in the denominator, which goes like 1/m². And when you expand out this geometric series, you get higher and higher powers of 1/m², right? So you see that the number of derivatives, the momentum is going to go up, right? It's never going to stay, it's never going to be bounded, right? It's going to be, if you go to spin S, it's roughly going to grow like, 1/m² to the 2s, to the S. So these are higher derivative and higher spin effective theories. And effective theories means that they have no massless limit, right? Because then this thing blows up here, right? So that's the best I can say for now, because these are not very familiar theories. So in order to construct this series, we have to basically write down an ansatz and do the hard work. But at least this series are very familiar, which is good. Now, what about this was this root Kerr theory, the gauge theory. What about the gravitational theory? Well, it turns out at 3 points, you can actually go back to this Quayle-Llewellyn-Tye formula, and you can just simply square your root Kerr amplitude in the appropriate way and get the gravitational theory. Now, you can do this in many different ways because you can basically decompose this spinning particles here in different ways. So there's a spin left and a spin right. So the way I prefer to do it is to say that one of them is spin 1 and the other one is spin S-1. And the reason for doing that is that gives the fewest number of derivatives. But it doesn't matter how you do it at 3 points, they actually gives the same answer. So that's an interesting feature. But using this, I can also write down a generating series for the gravitational amplitudes. It's a bit more cryptic here because I have now added the fermions to this and made it a bit more messy, but it's essentially the same formula, but there's some product of gauge theory factors. But from this, you can expand it out again and you can read off what are the interactions at low spin, and they turn out to be familiar series. So here I have a table which just summarizes what you get. So I don't have spin 0 in the table, but spin 0 is just an ordinary minimally coupled scalar. When you get to spin 1/2, you get a Dirac spinner in the root Kerr case and a Majorana spinner in the minimally coupled Majorana. why Majorana versus Dirac? Well, it has to be Dirac if it's charged, whereas a neutral particle can be Majorana. So I picked the smallest one, so that's Majorana. Then if you go to spin 1, in the Kerr case, you just simply get a minimally coupled vector, which is also known as Procca theory. But for the spin 1 gauge theory, it's not minimal coupled, right? It's non-minimally coupled, and it's precisely the interactions of a W boson. When you go to spin 3/2, in the gravity case, Kerr, you get a Rorita-Swinger Lagrangian, which is just the same thing as saying minimally coupled spin 3/2. That's what it is. But the Gravitino, again, is not minimally coupled, or sorry, in the gauge theory case. So this is not minimally coupled. So that's why I use different names for them. This is definitely a Gravitino from a gravity theory. This is just minimally coupled. Also Gravitino from a gravity theory, but in this case, it is minimally coupled. And if you go to spin 2, you can actually understand the massive spin 2 as a Kaluza-Klein mode. So in some sense, this theory is a truncation of a Kaluza-Klein theory. You can worry about whether this is a consistent truncation or not, but for the purpose of, for the amplitudes that we're interested in, which are essentially the 3-point and the Compton amplitude and so on, it is a consistent truncation. So you can start from a higher dimensional theory, look at one of the Kaluza-Klein modes, and that gives the interactions of that case. Now the rest, I don't know what they are. I'm just going to call it higher spin. They have more derivatives. So all of this series has either 1 or 2 derivative interactions, but these have higher derivative, higher spin interactions, right? All right. And here's a summary. Here's a summary of what you can do if you just stick to spin less or equal to 2. So in that case, you can always use the double copy. And so you can construct 5 different series: spin 0, spin 1/2, spin 1, spin 3/2, spin 2, using this double copy structure. And this should work to any multiplicity at 3 level. For example, if you want to compute this 5-point contribution, this should work. And interestingly, it is basically 1-to-1 to the multipole expansion. This is basically the Zurf, the monopole. This is the S linear in S. This is S squared, S cubed, S to the 4. And then, as I said, when you go beyond that, we don't know what's going on. And it's the same problem when you look at world line actions. People don't know what's going to happen after S to the 4, right? And so that's really what the problem is here, that there are some interactions, there are some spin multiple moments that are needed for PN calculations in the future, and they are at S to the 5 and higher, and we don't really know what they are, right? So that means that we need some new principles to fix this, or you can also be very smart and you can do a black hole perturbation theory, which I will mention at the end of the talk. That's another way to try to get what these are, but like the higher multiples are. But so far, nobody has quite done it in a convincing way. I think if I remember correctly, up to spin S to the 4 has been done, and well, let me not comment beyond that for now. Anyhow, so now let's talk about the framework of higher spin theories and see what we.
Henrik, maybe you go smoothly to conclusion, because we are a little bit over time. So
am I over time? Yes, I am. I guess yes.
Okay. Sorry for that.
Yeah. Yeah. Let me see. I guess I didn't expect it to take this long time.
I mean, we had the question, maybe 5 minutes. I mean, you can.
Okay, maybe about 5 minutes. Okay.
Oh, yeah, it's a little bit much, but let me do the beginning of the higher spin. Yeah, and then I will get into the conclusion after that. Yeah. so let's look at the series that we sort of understand, and let's check what are the properties of this series, right? So the most interesting ones are the ones that I listed here, right? So this is the Young-Mills plus a W boson, GR plus a massive gravitino, and GR plus a massive KK graviton. So what's interesting about this series is that they're all well behaved in the massless limit. You can take M to 0. And when you do that, they exhibit gauge symmetry. Or in other words, when the mass is non-zero, they exhibit spontaneously broken gauge symmetry, right? And so the symmetries that you get in the massless limit is simply non-abelian gauge symmetry, or also abelian if you do the abelian case. You get supersymmetry in the spin 3 half one, and you get general covariance in the spin 2 case, because this is essentially a KK graviton. So that's a very interesting property. Another interesting property that we found by looking into this is that we can construct something that looks like it looks like a ward identity of sorts. So we look at a current, and if you have a gauge symmetry, then if you multiply in the momentum of the current, you should get current conservation, right? But here it's just approximate current conservation. And I have shown what the current is. It's essentially this 3-point vertex with one leg of shell. So this is approximate, meaning that it goes like order M. And this is actually quite surprising because this vertex itself goes like 1 over M to some power. So why should it be that when you multiply P in that you get something that goes softly in M? But it's interesting that this has been studied by Peratti et al. And this condition comes from something that they consider to be a 3-level unitarity constraint. And so that's something that we also found that this series obey. Also, some of the higher spin cases. And essentially, the one way to think of it is that this is like longitudinal modes suppressed in the low mass or high energy limit. Now, let me skip this Lagrangians here because these are a bit messy. But let me say the next thing that we did, and this is the recent paper from December. So what we said is that, well, we already seen echoes of gauge invariance in the massless limit. We've seen echoes of spontaneous symmetry breaking. We've seen this current constraint, right? So it's part of a bigger framework. So the bigger framework is higher spin gauge invariance, and anybody working on higher spin, they hold this very dear, right? So, what we're going to do here is that we're going to look at spin 2 root Kerr case. So this is our spin 2 physical field. What we're going to do is we're going to introduce Stuckelberg fields, just like you do for the spin 1 case. And then you can write down massive higher spin gauge transformations, which are linearized. They're linear in the gauge parameter, and you can also say that they are first order in the fields. Xi here is the gauge parameter. And you can ask what good does it do? Let's say you find a Lagrangian which respects this symmetry. Well, usually it does 2 things good. One thing is to say that the degrees of freedom are correct, because now we have introduced extra fields, and you might worry about the degrees of freedom, but the degrees of freedom are correct if you have massive higher spin gauge invariance. Moreover, you should expect that in a small mass limit, there should be something which is better behaved than naively expected. We know that that's how it works in the W boson case. We know how that works in spontaneous symmetry breaking and so on. Now, maybe I should skip the details here because this is just an example. And I should just comment here that we actually did it for any spin, not just spin 2. And we used a framework which was only written down 2001. So this is a fairly recent higher spin framework by this Russian guy, Sinyovev. So what we did is that we introduced a tower of higher spin fields. So that goes from 0 to spin S. So this K here is basically the number of Lorentz indices. You have an equal tower of higher spin gauge parameters, which are traceless. These are double traceless. And then what you can write down is you can just write down the whole gauge transformation in one equation. And these are just some numbers, depending on what S and K are. You can write down a minimal Lagrangian is basically Syniova's Lagrangian, but we have written it in a very suggestive way. So we have pulled out a Feynman gauge part and the gauge fixing part, and that just makes it very easy to write down. So this is the gauge fixing function. This is the Feynman gauge Lagrangian. So after you have subtracted out this piece, and as you see, it's very simple. It's just the box operator on higher spin fields. This is the trace of the higher spin field because, well, you can take one trace, but not two traces. This is the minimal interactions. Now you have to add non-minimal interactions. This ones you get from just covariantizing that Lagrangian. This you get by an ansatz. And I'm not going to explain this here, but we had a set of constraints. One of the constraints was word identity. One of them was the current constraint that I already mentioned. Third one was power counting bounds. You always have to limit the number of derivatives. If you don't do that, well, then anything goes. So we imposed that. This one, maybe I shouldn't discuss this. It's something that we did for technical reasons, but in the end of the day, we noticed that it's probably not needed. It's certainly not needed for gravity, so let me not talk about it. The conclusion of doing this exercise, which we did to very high spin, is that it gives unique Kerr and root Kerr 3-point amplitudes, and they match exactly Akani Hamed, Huang, and Huang. So this means that there is a unique theory here for different S, but they're all satisfying a certain set of properties, which most people will say are nice properties, and it gives uniquely Kerr, right? So there's something very special about this series. As we saw at low spin, there's vanilla series that we anyhow use in quantum field theory, right? These are all the theories that we usually encounter. We also wrote down a propagator. Let me not talk about that. We wrote down an amplitude for the Compton process, which had a spurious pole. So this one does not have spurious pole, but we still have some undetermined contact terms. We did parameterize it, and we found that it is constrained, but we still do not know what it is for spin 2 and higher. Okay, so now I'm at my summary slide. So sorry for going over time, but the conclusion of this work is that we did a lot of exercises convincing ourselves that this massive higher spin gauge symmetry is a really good property that seems to pinpoint the Kerr dynamics at 3 points for all spin, and it also gives back the known formulas at a 4-point Compton level in the cases that we know. It also seems to predict some new constraints at the Compton level, and I should say we only scratched the surface so far. We don't know if it uniquely predicts the Compton. It might uniquely predict it if we just add some other constraints, or if we are just thinking about it in a more clever way, But there are further checks needed, of course. I mean, we're not saying that this is obviously the right thing. It's not at all obvious. So, for example, what needs to be done is one needs to compare to honest calculations, so honest black hole perturbation theory calculation, which are using the Tukosky equation. People have done those calculations, but they're extremely complicated, and as far as I understand, at least, and so we don't actually have amplitudes to compare to. One can also study the classical limit in more detail and maybe infer that classical limit has to have certain properties. Maybe there's a Newman-Janis shift at the Compton level. Nobody has ever suggested that, but it is there at 3 points, so why shouldn't it be there at 4 points or some echo of it at least? And then another question is it unique at 4 points? We don't know. That's something that needs to be studied. Maybe some implication for quantum black holes, maybe including absorption and emission. Maybe I should end there. And if you have questions, I'm happy to answer them.
Okay, thank you very much.
Thank you.
Your very interesting talk, many details you present for us. Questions, please. Slava Didenko. I see Slava Didenko has a question. Please ask.
Okay, thank you. Thank you for a very nice talk. I have a sort of vague question, but maybe your comment would be very useful. So this idea of higher spin symmetries in Kerr solution is very attractive from different perspectives. But one thing looked puzzling. So from your talk, you suggest that amplitudes reveal massive higher spin symmetry. But on the other hand, if you look at double copy construction, which you extend to higher spins, and it better if you consider the ADS case, then you will see that Kerr solution generates massless higher spin gauge symmetries. And those two things together in the same dimension looks kind of, I mean, it's not a deformation of the symmetry, it's just breaking of them. Do you have in mind how to reconcile those two pictures?
No. Yeah, I know that higher spin community and I guess in general, people like the massless case better, I suppose, right? But maybe in curved space, I guess. But to me, living in flat space, I have trouble understanding the massless case. So I don't really have a good idea. I think you're much more of an expert on this than I am.
So maybe it could be related to the fact that ADS scale somehow transformed to massive scale in your language. Maybe
indeed, yes. That's I have some vague ideas along those lines, but they're very naive. Okay. If you're probably familiar with the Sinova paper, I mean, he was motivated by doing massive ADS or massive curve space, right? So we just set the curvature to 0. That's what we did, right? And then we could recycle the formulas. Yeah.
Okay. Thank you.
Okay. I see a question from Oleg Tiryaev. Oleg, please ask your question.
Well, thanks for an interesting talk, and I have a couple of naive questions. Your representation of graviton amplitudes looks like a density matrix for the spin 1. And my question is, how far can you move? Can it possible to go with this analogy? Say, use density matrix positivity. And in particular, it looks natural that gravity wave polarization looks like Stokes parameter Xi1 and Xi3, and there is no circular polarization. And second question related to that, if one consider the coupling to matter, this somehow supports representation of energy momentum tensor like a product of two vector current, which is known as, I believe, Sugawara construction. Is there any relation to that?
Yeah, I guess there are relations, but maybe just superficial. I think it's, I mean, maybe it's just the fact that you can get higher spin representations by tensoring lower spin representation, but of course, I mean, Sugawara is much more non-trivial. So the details I don't know. Yeah.
But is it possible to use density matrix positivity at least?
Yeah, unfortunately, I think all the questions you ask me are things that I'm not really expert at answering. So I think it sounded very interesting. I also don't know exactly which formula you were talking about.
Well, just your very general representation as a product of two polarization vectors, because if it is bilinear, this is a density matrix, right?
Yeah. I think I think there's many ways to understand this. I guess you're talking about the double copy, right? Yeah.
Well, exactly. Just this double copy looks like this is, in a sense, amplitude is already a sort of probabilistic one.
Right.
Just it's already looks like a density matrix. So it looks like just for spin 2, Just if there are two polarization vectors, it's sort of probabilistic. If there are more, it looks too many for this.
I think I'm starting to understand what you're asking. Yeah. I mean, you're asking essentially that. I think it's related to asking about cross sections, right? That
in a sense, yes. Already amplitudes looks like it's already a cross section.
Right.
You mentioned that it is that the S matrix element looks like just a cross section. So this is related to that. That maybe it's possible to explore some facts from density matrix, just properties here. If so, this would be interesting.
As far as I know, there's no obvious, or there's no work that trying to, write the double copy in terms of cross section. I mean, one thing is that when you compute a cross section, you're supposed to complex conjugate there.
Absolutely, and because of this in particular, to have. If you consider this as a density matrix of photon, there is no just complex inputs corresponding to sigma 2 density Pauli metric. So there is no circular polarization. I think it's a good explanation why we don't have a circularly polarized gravitational waves.
Right.
Yeah.
Maybe for external scalars, maybe it could be some relation to density matrix. But I think for gravitons, and it's probably less easy to explain it in terms of that language, I guess. Yeah.
I see. Okay. Yeah. Thanks.
Yeah, you're welcome.
Yeah.
Okay. More questions, please. More questions? I don't see more questions. If there is no more questions, let's thank our speaker again. We are. Okay. The talk was more than 1 hour, so maybe people are tired. Yes.
Yeah.
Thank you very much once again for very.
Thank you, Henrik. It was very nice.
Thank you very much for inviting me.
Thank you. Bye-bye.
Bye-bye.
Have a nice evening. See you, Henrik.
Please don't forget to send us your transparencies.
Okay. Yep, I will. Thank you.
Thanks, Henrik.
Thank you very much.